Hi, welcome to the Pixelligent presentation on high refractive index nanocomposites for light extraction in OLED lighting. I'm Greg Cooper, founder and CTO of Pixelligent, and today I'm joined by Matt Healy, our VP of Product Management.
We're going to start with highlights on Pixelligent, and then continue our presentation with the details of our nanocomposites for OLED lighting. Pixelligent is an advanced materials company. We leverage nanotechnology to deliver improved performance in LED, OLED lighting, and in various optical coatings and display applications. Pixelligent Technologies was founded in 2000 and has grown to a team of nearly 50, including Ph.D. chemists, polymer scientists, and application engineers. Pixelligent's headquarters are located in Baltimore, Maryland, and features sophisticated research and development resources and a pilot manufacturing facility. Pixelligent is a leader in zirconia nanocrystals and produces the best dispersions available. We do this by carefully controlling the synthesis, capping, and dispersibility of our materials. The result is high-quality, monodispersed particles that can be highly loaded into a variety of polymer systems. As seen in the TEM on the right, Pixelligent synthesized zirconia is produced with very narrow size distribution without agglomeration. In the insert image on the upper right, you can see the particle crystallinity. In the bottom image, 58% zirconia nanocrystals and xylenes are shown next to pure xylenes. There is no visual difference. With unique capping agents, zirconia nanocrystals can be added to polymer systems at very high loadings while maintaining monodispersion and transparency. Our process is highly scalable. We now have multi-ton capability for our materials. Over the past 15 years, Pixelligent has developed a strong IP portfolio to support our commercial activities. Pixelligent operates from our headquarters in Baltimore, Maryland in the U.S. We manufacture here in Baltimore at the pilot scale and through a manufacturing partner for large-scale production. For us, pilot scale is up to 5 metric tons per year, and larger scale is up to 40 metric tons per year. We serve a global customer base from Baltimore, a large portion of our customers in Asia. More than half of our market presence is in the solid-state lighting sphere, which includes LED and OLED lighting applications. Pixelligent has scaled the process for creating its PixClear nanocrystals while maintaining high material quality. In this slide, we walk through the manufacturing process. First, the zirconia is grown in the synthesis step. Then it is capped with materials that allow compatibility with the desired application. In the last step, the capped nanocrystals are purified and added to their final dispersion medium. Each step in the process to produce Pixelligent zirconia nanocrystals occurs in the liquid phase, which ensures quality and safety for our process. Regulatory requirements for shipment in the U.S. and internationally have been addressed, and we are proud to announce that our capacity for zirconia nanodispersions will be 40 metric tons, starting in the first quarter of 2016. Throughout the process of increasing our capacity to produce nanocrystals, we have focused on ensuring the quality of our materials. All of our products are verified with strict quality control standards, and on this chart we show some of the representative data for one of our products, PCPA, for particle size, optical density, D99.99, which is a measure of the monodispersity of our products. As you can tell, the process we use to create our nanocrystal is extremely stable, as the data in these charts cover manufacturing runs over several years. In this slide, we look at the effect of adding zirconia nanocrystals to an acrylic system. The chart on the left shows a base acrylic polymer with a refractive index of 1.58 at 450 nanometers. As you can see, as more zirconia is added to the film, the refractive index increases as the volume percent of the zirconia increases. In this case, we show nanocrystal loading concentrations from 0 to 90 weight percent. The resulting refractive index increase from 1.58 to 1.83 at 450 nanometers shows the wide range of refractive index tunability that Pixelligent's nanozirconia dispersions enable. Pixelligent zirconia-loaded systems produce tunable increases to refractive index without interfering with desirable optical qualities. This is an important feature for refractive index matching applications that aim to improve light extraction. In the plot on the right side, the transmission of a polymer system at 350 nanometers is shown to modestly improve with greater amounts of nanocrystal loading, while the transmission at 650 nanometers remains near 100% throughout all nanocrystal loadings. Similarly, in the table on the upper right, absorption and haze are minimally impacted by nanocrystal loading up to 90 weight percent.
Because of the planar nature of OLEDs and the fact that the light is created in a high index region, about 75% of the light that is created is trapped in the device due to total internal reflection. Some of the light will escape naturally, but the rest needs to be redirected to get it out of the panel. Because of the significant potential for improvement in performance, researchers have devoted a great deal of effort to figure out the best extraction schemes. These approaches vary in where and how light is redirected. Currently, most manufacturers use external extraction, which offers a greater than 60% improvement in light output and is very easy to manufacture as it simply involves attaching a film to the outside of the OLED. Unfortunately, external extraction only has access to about 50% of the total light generated, so its potential for further improvement is limited. Because of this, there is broad agreement that for the next generation of products, the ITO substrate interface is where light should be redirected, and that scattering is how light should be redirected. This approach has access to the most light with minimal impact on device performance. It also offers the most mature manufacturing process of any improved light extraction approach. With light extraction, we need to think about both performance and manufacturability. With performance, we think about light extraction as a function of angle and wavelength, including potentially control of étendue, whether the light extraction layer is flexible or rigid, and the spatial uniformity across the panel. With manufacturability, we need to think about the number and cost of manufacturing steps as well as the yield and repeatability of each of those steps. Obviously, we would like to have light extraction that has high performance and is easy to manufacture. As with most things, in order to get high performance, we need to use high performance materials to make complicated structures, which reduces manufacturability. So there is an inherent trade-off. Pixelligent has developed a roadmap that includes 4 generations of internal light extraction products. While the different generations differ in the details of their internal structure, they are all based on Pixelligent's solution processable, high refractive index nanocomposites and are compatible with commonly used low-cost, high-performance manufacturing equipment and processes. Our Generation 1 product is a high-index smoothing layer for covering customer-supplied light extraction features. Most light extraction features are rough and do not provide a suitable surface for depositing the OLED stack. Pixelligent's solution processable nanocomposites create a smooth surface which is suitable for the OLED stack. That surface needs to have a high refractive index so that the light generated in the stack can be effectively coupled to the light extraction features. This may eliminate the need for external light extraction. In August of 2015, we launched a family of Gen 1 products. Our Generation 2 product incorporates the light extraction feature, in this case scatterers, directly into the high index layer. Compared to our Gen 1 product, this offers a simpler manufacturing process because there is no longer a need for a separate manufacturing step to create the light extraction features. Distributing the scatterers throughout the high index layer should also allow for more efficient extraction. A beta version of our Gen 2 product is now available for sampling under NDA. The Gen 2 light extraction layer has demonstrated a significant improvement in external quantum efficiency compared with no extraction and external extraction. For this demonstration, Pixelligent deposited our Gen 2 layer using a slot die coder. These films were cleaned and ITO in the device were then deposited. The Gen 2 layer more than doubles the light output compared with no extraction, and adding external light extraction does not further improve the extraction efficiency. Our Generation 3 product incorporates a graded index in the Z direction, which will further improve the efficiency compared to Gen 2, but offers a more complex manufacturing process. Pixelligent is currently developing materials and manufacturing processes for Gen 3. Our Generation 4 product has a 3-dimensional graded index, which could include but does not need to have scatterers. This approach will offer the highest efficiency, but will also have the most complex manufacturing process. The Gen 4 layer will also offer the ability to direct the light output of the OLED panel. That is, it will be able to create non-Lambertian distributions, a unique feature of the Gen 4 structure. This will be the subject of future work at Pixelligent. One of the major advantages of the Pixelligent approach to making light extraction layers is the flexibility of the manufacturing process. Pixelligent's formulations can be deposited and patterned with many common deposition and patterning methods, including slot die, spin coating, inkjet, spray coating, and UV patterning. Our formulations are also compatible with many different substrates, both flexible or rigid, and film or glass. This flexibility is especially important considering the early stage of OLED manufacturing. Different OLED panel makers have different manufacturing processes with different material sets for different applications, and the Pixelligent approach allows for customizable solutions.
To give further insight into our technical development roadmap, we prepared a timeline of our OLED products. We made our Generation 1 materials available last year and launched a broader family of materials in August of this year. Pixelligent currently offers high refractive index formulations as well as custom OLED products for light extraction. Very recently, we made our 2nd generation formulations that include scattering particles available for customer testing under NDA. In the future, we will launch our Generation 3 and Generation 4 materials in 2016 and 2018.
In summary, Pixelligent is using zirconia nanocrystals to create better OLED lighting. We are the leader in the production of high-quality commercial-scale zirconia nanocrystal dispersions. One important use for these dispersions is to make solution-processable nanocomposites whose properties can be tuned by controlling the loading of the nanocrystals. These nanocomposites can have combinations of properties, for example transparency and refractive index, that are unachievable with pure polymers while retaining the processability of the polymer system. We are using these nanocomposites to create 4 generations of highly efficient internal light extraction layers for OLED lighting. These light extraction layers can be manufactured using a variety of low-cost, high-performance deposition and patterning processes that are compatible with different OLED manufacturing approaches.
This concludes the presentation on Pixelligent zirconia nanocomposites for OLED lighting. On this slide, we show our contact information if you have any additional questions. Thank you for listening.